Hello, welcome to the glass plate. In the example of this video, we're going to take a look at flow through a cylindrical tube, but this tube is not horizontal, it is sloped. The length of the tube is 100 meters and the height, the drop h, is 4 meters. So I made an exaggerated drawing. The diameter of the tube is 10 centimeter and the roughness of the tube is 1 millimeter. So this is not a smooth internal wall material of the tube. Water is flowing through this tube in and out in a steady state, and we assume that here is atmospheric pressure and here is atmospheric pressure. So we ignore inflow and entrance and exit effects. And what we would like to know is what is the water velocity, the average velocity in this tube. So far we've been dealing with situations where we have a pressure drop and that gives rise to a flow balancing friction. So this is the driving force and this is the frictional force, if you want, with Fanning's friction factor, to make this real numbers. Okay, but now I can't use this because delta P across is 0. Nevertheless, we do know that the water will start flowing from the higher to the lower point, and thus I need to rethink how to do this. Well, how did we arrive at this? There was via a mechanical energy balance, which in steady state reads as what comes in minus what goes out in terms of the mechanical forms, minus the production, which is the dissipation of mechanical energy modeled as phi m times E sub Fr, the amount of energy per kilogram dissipating during the flow. And this rule gives you a handle on dissipation versus the driving forces. Now, for our tube, which has a constant diameter, the inflow velocity just inside the tube here at position 1 is equal to that of position 2. They are both the velocity v, so this is a 0. Whereas the pressure at the entrance and the exit is also the same, so this is a 0. But this one isn't. This equals g times h, the height difference. The driving force is no longer pressure, but it's potential energy, gravity energy. And I can use the same idea, because this is friction with the wall, and that is still, regardless of how the flow is driven, for F L over D half v squared, not rho v squared, but that's because of the units. Okay, so now I need to solve this equation and I can back out the velocity formally written as v equals the square root of 2 times gh divided by a d and an l and a 4f. It's just equating these two because the phi's drop out. Let me check for a second. Yep. Okay, what's the problem here? This is a function of the Reynolds number and thus of the velocity that I don't know. But we've seen this before. just like when determining the terminal velocity of an object that I drop down, for instance this pen, then the velocity can be written in terms of gravity and not a fanning friction factor, but a drag coefficient, and the drag coefficient is a function of the Reynolds number. Same idea applies here. I'm going to solve this iteratively. So I take as a guess water velocity meter a second. Then I can compute the Reynolds number, rho v d over mu for water, 10 to the third in IS unit, 10 to the minus 3, 0.1, and the 1 for my gas is 10 to the fifth. Together with the given roughness, which has an epsilon over d as the relative roughness of 10 to the minus 2, I can read the F over 2 graph versus Reynolds, which is something like this on a log-log scale, the linear part, and then here you got those multiple curves depending on epsilon over d. You read that off at Reynolds equals 10 to the fifth. You look for the right, say that is this one, curve, epsilon over d being 10 to the minus 2. And then you read off what F over 2 is. And that gives F over 2 is 0.004 from the graph that I inspected. Thus I can rework this, fill in F over 2 here, so the F, compute again, everything else is known, and I get my first estimate of V after my initial guess, and it gives me, if you put in the numbers, 1.5 and a bit meters a second. And then I need to iterate. So I again compute Reynolds, which is now no longer 10 to the fifth. This one is 1.5, so this is about 1.6 10 to the fifth. And I read off my Reynolds versus fanning friction graph. And for this relative roughness, this line is already pretty flat. So if you read it off, you find by and large the same fanning friction number, and thus the iteration is closed. And here is your answer, just like we did. Okay, recapturing. What I did is realizing it's not a pressure difference, it's a gravity difference that drives this flow. Mechanical energy balance can be used provided you can assume no in and out effects. Later on we'll refine this in the course. And then get a formal expression for V, which contains a function of V itself. Use an iterative approach, read off the graph a few times, do the calculations, and you find the answer.